Hello everyone, welcome back again to LFI Educates. In our physics class, today we are going to discuss about Lensmakers formula. This is a formula that exists between the focal length of a lens, the refractive index of the material of the lens, and the radius of the two radius of curvature R1 and R2. This formula is popularly known as Lensmakers Formula. While manufacturing lens, this formula is used. So don't get confused with thin lens formula. Thin lens formula was 1 by V minus 1 by U equal to 1 by F. This formula is not used for manufacturing lens. This formula is used to get a desired focal length of a lens. What should be the curve, or how the curve should be, it will depend upon the radius of curvature R1 and R2 and what material you are using it. That will be decided by this refractive index. Then you will get a desired focal length as you wish. Now to derive this relation, Lensmakers formula, we take a convex lens this way, then we will draw the principal axis. We will take one point object towards our left hand side, let it be O. The first ray that will go straight, passing through the optical center, will go undeviated. Let me mark it as X. Now in the second ray, let us take the ray obliquely this way. First it will come and strike the first surface, let it be X, M. Here also I wrote X, let it be P. X, M, Y, let it be. And it said X, N, Y. The first ray will go and strike. At this point, if you draw the normal perpendicular to the surface, then this point will be marked as C1, the first center of curvature, and distance from pole up to the first center of curvature, we'll call it as radius of curvature, R1. Then as the light is passing from rare medium to denser medium, in the first, it will come like this. Here the image will be formed, but this is for the first surface, so we'll take it as the image of the first surface as the virtual object for the second surface. When it comes and strikes here, then again light is traveling. Here also you will draw one normal passing to the center of curvature. Here it will be C2. This distance C2 up to P, we will call it as radius of curvature, R2. At this point, again light is striking from glass to air, so from denser to rarer, it will go away from the normal, so it will come like this, and the final image will be formed at I. That will be your final image. So I can mark this as V. Now for the first surface X, M, Y, you can start like this. For the surface, for the spherical surface, X, M, Y, you will use your formula that we have derived for spherical surfaces. So here air, so refractive index of air, will take it as mu1. This is glass, refractive index will take it as mu2. And again this is air, so refractive index will take it as mu1. Now mu1 divided by object distance. This is your object distance from O to P. This is your object distance. Mu1 divided by OP, or for the surface when you say XMY, we'll write OM, plus mu2 divided by image distance. Image distance is from M to I dash. That is your virtual image. We'll take it as V dash. That is your M I dash is equal to mu2 minus mu1 divided by radius of curvature. For the first surface XMY, radius of curvature is R1. This R1 means it is from M to, initially we'll take from M to C1. M C1. But M is very close to P. As the lens is very thin, this P is coinciding with M. So this M, you can replace it. OM will be equivalent to OP. MI dash will be equivalent to PI dash, and MC1 will be equivalent to PC1. So substitute it here. Mu1 divided by OM will write as OP plus mu2 divided by PI dash equal to mu2 minus mu1 divided by PC1. We'll mark this as equation number 1. Now, in the second case, when you take the spherical surface X and Y, light is entering from mu2 to mu1. So we'll write like this. For the spherical surface, X and Y, light is entering from mu2 to mu1. So you start with mu2, here you write mu1. mu2 divided by object distance. Now this time the object for this surface is the virtual object, is I dash. So it is I dash n. I dash n plus mu1 divided by the image formed by this surface is I. So it will be ni. That is equal to mu2 minus mu1 divided by radius of curvature. For the second surface, it is here R2. So write NC2. NC2. Here also N is very close to P. So this N will be replaced with P. But N is very close to P. Therefore, N is very close to P. Therefore, I dash N will write it as is nearly equal to I dash P. Ni will be equal to Pi, and Nc2 will be equal to Pc2. But here one thing you have to mark. This refractive index mu2 and I dash n, they are in other direction. mu2 is here inside the glass, and I dash is, the object is this side, the other side. As they are on the reverse side, here you have to take one negative sign. Then if you put these values here, you will get minus mu2 divided by I dash n will be I dash p plus mu1 divided by pi will become pi, that is equal to mu2 minus mu1 divided by nc2 will become pc2. Let us mark this as equation number 2. After getting these two equations 1 and 2, we'll add them up. When we add them up, adding equations 1 and 2, we'll get these two terms. You can see mu2 by pi dash. Here one is minus mu2 by pi dash and one is plus, will get cancelled. So mu1 by OP plus this one mu1 by pi is equal to right hand side mu2 minus mu1, left hand side also, right hand side in equation 2 also mu2 minus mu1. mu2 minus mu1, you take it as common, and in the bracket you can write 1 by PC1 plus 1 by PC2. Then if you take common mu1 here, 1 by OP plus 1 by PI is equal to mu2 minus mu1 divided mu1 into 1 by PC1 plus 1 by PC2. Then this mu1 term, if you bring it down, you will have 1 by OP plus 1 by PI equal to mu2 by mu1 bringing down, minus here mu1 by mu1 will give you 1 by PC1 plus 1 by PC2. And this one we can write it as 1 by OP plus 1 by PI is equal to refractive index of second medium with respect to first. 1 by PC1 plus 1 by PC2. Now after this we'll use sign convention. Let us mark this as equation number 3. We'll use sign convention. Using sign convention, here OP is equal to object distance, it is towards our left hand side, so we'll take it as minus U. PI is the final image, that is V from here to here, P to I. Final image is on the right hand side, so it will be positive. PC1 is the radius of curvature for the first curve, it is on the right hand side, so we'll take it as plus. And PC2, P to C2, from P to C2 it is towards our left hand side, so R2 will be negative minus R2. Using these sign conventions, if you plot it here or put it here, 1 by minus U plus 1 by V is equal to refractive index of second with respect to first, 1 by R1 minus 1 by R2. Like this you will get it. Or more nicely, if you write down 1 by V minus 1 by U is equal to refractive index of second with respect to first, 1 by R1 minus 1 by R2. Now, one assumption we will do, whenever the object is kept, this one let us mark this equation number 4. The assumption is that when an object is kept at infinity, when an object is at infinity in a convex lens, we know that when the object is kept at infinity, the image is always formed at the focus. The image is at the, or the image is formed at the focus. Now if the object is kept at infinity, then it's U. When, or that is, the meaning is, when U is at infinity, the image is formed at the focus. This concept we will put it here. Now if we put it, this concept here, then this 1 by F, it will become 1 by V will become 1 by F. 1 by F is minus 1 by undefined is 0. So this term will turn out to be 0. That will be equal to mu21 minus 1 into 1 by R1 minus 1 by R2. This is your Lensmakers formula. This way you can derive it. Sometimes you are asked to prove or you are asked to find out thin lens formula from this Lensmakers formula as well. Derivation of thin lens formula using Lensmakers formula. Now if you are deriving Lensmakers formula, then it is easy to write down that from equation 4 and 5 by equating we will get the answer 1 by f equal to 1 by v minus 1 by u. But if they ask you only to get the Lensmakers formula, from Lensmakers formula to get the thin lens formula, then at that time you are not deriving it. So you have to remember these two equations 4 and 5. You can start like this. Lensmakers formula is, or from Lensmakers formula, one by f is equal to mu minus 1 by r1 minus 1 by r2. This one will mark this equation number 1. Then for biconvex lens, you can write 1 by v minus 1 by u is equal to mu minus 1 by r1 minus 1 by r2. This one, this is from equation number 4. Simply by writing these two equations, you can equate them. Equating equations 1 and 2, right hand sides are equal, so left hand sides also will be equal. 1 by f is equal to 1 by v minus 1 by u. This way you can get your thin lens formula from Lensmakers formula. It is in the process of derivation. Just you have to compare these two equations and get the thin lens formula. Now let us discuss about the dependence of focal length on refractive index. In our earlier discussion, in Lensmakers formula, 1 by f is equal to refractive index of second medium with respect to first minus 1. When we are talking about focal length and refractive index, you'll have to concentrate here. Forget about the radius of curvature. Suppose this is refractive index of glass, this is refractive index of water, refractive index of air. Mu2 is 1.5, refractive index of air is 1. So here you can see that you get a positive result, 0.5. This is plus. Now, if I take a liquid whose refractive index with respect to air is less as compared to the refractive index of the material of lens with respect to air, then its focal length will increase. You can see you get a positive result. If this second medium refractive index will become more compared to the liquid where you are dropping the lens, then the refractive index will increase. It will increase. If you dip a convex lens inside the medium, then its focal length will increase. If you take a concave lens and you dip it inside a liquid whose refractive index is less with respect to air, then the material of which you have made the lens, then its focal length will increase. And in the second case, if the liquid that you are going to immerse the lens, if the liquid has higher refractive index with respect to air compared to the refractive index of the material of the lens with respect to air, then the focal length will become negative. In that case, a convex lens will behave like a concave lens and a concave lens will behave like a convex lens. Then in the third case, here it will decrease, it will become negative. When I say it will become negative, then you should understand that convex lens focal length is positive, So it will become negative focal length. That means convex lens will behave like a concave lens, and concave lens, we know focal length is negative. So if it changes to negative, then negative of negative is positive. So concave lens will behave like a convex lens. Then in the third case, if the liquid that you are immersing the lens has the same refractive index with respect to the lens itself, then the lens will become invisible there and it will act like a plain glass sheet. It will act like a plain glass sheet. So these 3 points, a very important concept you need to know. Let us do this numerical and see. The radii of curvature of the surfaces of a double convex lens are 20 and 40 centimeter. The first radius of curvature is 20 centimeter and the second radius of curvature is 40 centimeter. While doing the Lensmakers formula, you have seen R1 is on the right hand side, so it is positive. R2 is on the left hand side, so we take it as negative. We use the Sine Convention respectively, and its focal length is 20 centimeter. Focal length of convex lens is positive, so I am taking it as plus 20 centimeter. If it is a concave lens, we take negative. What is the refractive index of the material of the lens? You have to find out the refractive index of the material of which the lens is made up of. Refractive index asking. So using Lensmakers formula, one by f is equal to mu minus 1 by r1 minus 1 by r2. This is your formula. If you put the values, 1 by f, that is 20, is equal to mu to find out, just keep as it is. 1 by r1, it is 20, minus of minus, it will become plus 1 by 40. Then this is 1 by 20 is equal to mu minus 1. LCM of 20 and 40, 20 and 40, 10 is common, 2, 4, 2, 1, 2, 2, 4 tens are 40. You will get 40, 22 times plus 40 one time. So you will get 1 by 20 is equal to mu minus 1, 3 by 40. This term we cross multiply here, 1 by 20 into 40 by 3. 22 times is 40. It is mu minus 1. Now, this 2 by 3. This side you have 2 by 3, or you can write mu minus 1 is equal to 2 by 3. So mu will be 2 by 3, minus 1 will become plus 1. 2 plus 3 by 3, if you take LCM, it is 5 by 3. Like this, you can find out the refractive index of the material of the lens. Now let us discuss about power of a lens. Power of a lens, what it is, then we will say that it is the capability of a lens either to converge or to diverge the rays. You can see here one diagram, the capability of the lens to converge here is more. So the power will be more. And in that case, the focal length will be less. And if the capability of the lens to converge, its converging action is less, then the focal length will be more and the power will be less. Power and focal length, they are inversely proportional to each other. We measure power with this formula reciprocal of focal length. The same in case of concave lens also. The capability of diverging, here you can see the capability of diverging is more. So the power will be more and the focal length will be less. But in this case you can see the capability of diverging is less, so focal length is more. And if the focal length is more, automatically the power will become less. Now how do we define it? Let us see. You know what is power now? Power is the capability of converging or diverging a ray of light through the lens. How do we calculate power of lens? Then you say power P we measure as the reciprocal of focal length in meters. The focal length must be in meter, and the SI unit of power is diopter. Now how we can define it? Let us see. Power of a lens is defined as the tangent of the angle that is made by the light ray while converging or while diverging in case of concave lens, if the ray has struck exactly at a unit distance from the optical center. We define like this: tan theta, or here it is tan del. It is equal to, this is your focal length f, perpendicular by base h by f. For small angles, tan del is equivalent to del. If this point at which the light ray has struck is at a unit distance 1, if you take, then you get the reciprocal of focal length. So this term we call it as power. When measuring power, we use del as power, and that is equal to 1 by f. Now let us study about combination of two thin lenses in contact. Combination of two thin lenses in contact. Now here what you will do is, you will try to find out the equivalent focal length of the lens after the combination. Suppose these are the two thin lenses I am taking as lens 1, and lens 2 I will draw it later. So when you draw the diagram, take the object here, let the ray pass through the center of the first lens, optical center of the first lens, it will go straight. The second ray, if I draw it obliquely, then it will converge and form an image. So I can take the lens formula this way. For lens L1, 1 by V minus 1 by U is equal to 1 by F. So here this image is going to become the virtual object for the next lens. So instead of writing V, I'll write here V dash. This is a virtual image of the first lens. This is the image of the first lens. This is the object distance U. So I'll write this as V dash. 1 by U equal to 1 by, let us take the focal length of the first lens as F1. I'll write equation number 1. Now if I bring another lens in contact with it, another thin lens with focal length f2, lens is suppose L2, then this ray after coming here again will converge and will get the final image here. So the earlier one I read I dash, and now it will become I. So if this distance, will take it as the final image V. So if I take the second lens L2, then again I will use 1 by V minus 1 by U equal to 1 by focal length is F2. But in this case the image is V, find 1 by V minus 1 by U. U will be replaced with, this is the virtual object I dash that you can see here. So this V dash, so this U will be replaced with V dash. This will mark this equation number 2. On adding these two equations, one and 2, you will find that 1 by V dash, that is minus, and 1 by V dash, that is plus, will get cancelled each other. You will have 1 by V minus 1 by U. 1 by V minus 1 by U is equal to 1 by F1 plus 1 by F2. We are adding it. Now, if F is the equivalent focal length, of the two lenses in combination, then 1 by f will be equal to 1 by v minus 1 by u. Let us mark this as equation number 4 and this one as equation number 3. Now if you compare this equation 3 and 4, in place of 1 by v minus 1 by u, you can replace it with 1 by f. From equation 3 and 4, you can write 1 by f is equal to 1 by f1 plus 1 by f2. So f here is the equivalent focal length and you measure it like this. 1 by f is equal to reciprocal of the focal length of the individual lenses. But here you have to be somewhat careful. If the first lens is convex, okay, is positive. If this is concave, then it should be here minus. Focal length of concave lens will take negative. Focal length of convex lens will take positive while doing the calculation. While deriving, we are taking both as convex lenses. Now from this you can get the expression for power as well. If 1 by f is equal to 1 by f1 plus 1 by f2, then the focal length of the power of the combination combined lens will be equal to power of the first lens plus power of the second lens. Here also, if lens is concave, minus will come out. If lens is convex, plus will be there. And if the first one is concave, negative. If the second one is concave, negative. So concave lens will get negative power, negative focal length. Convex lens will get positive power and positive focal length. You can even get one more relation here. Your Lensmakers formula 1 by f is equal to mu minus 1 by r1 minus 1 by r2. This one also is an expression for power. You can calculate power with this formula as well. 1 by r1 minus 1 by r2. Let us see one question like this. Magnification produced by combination of lens. The equivalent magnification will be magnification produced by the first lens multiplied by magnification produced by the second lens. Then if 3-4 more lenses are there, then it will be M3, M4, M5 and so on. As well as if the two lenses are kept at a slight distance from each other, if the gap between the two lenses is suppose say D, then in that case your equivalent focal length, reciprocal of the equivalent focal length will be equal to 1 by f1 plus 1 by f2 minus d divided by f1 f2. Let us solve this question and see. Two thin lenses are in contact and the focal length of combination is 80 cm. Let f be the focal length of the combination, or you can write down, you know already that f is the focal length of the combination, that is 80 cm. In meter it will be 80 divided by 100, that is 0.8 meter. You can write like this. If the focal length of one lens is 20 cm, focal length of the first lens is given, it is 20 cm. In meter it will be 0.2 meter. Then what will be the power of the other lens? You are asked to find out the power of the other lens. Other lens means we'll take it as P2. P2 is how much they are asking you. So what we'll do is, from here, focal length of the combination, we know that power P of the combination will be 1 by the equivalent focal length, that is 1 by f, it is in meter. It is 1 by f is 0.8, it will be 10 by 8, 2, 4 times is 8, 2, 5 times is 10, so it will be 5.5 by 4. SI unit of power is diopter. Like this, to find out the power of the combination. Then in the second case, we can find out the power of the first lens. Also, P is equal to 1 by P1, this is for the first lens, 1 by f1, there is 1 by 0.2, this is also in meter, so it is 10 by 2, this will give you 5 diopter. After finding this one, you can use the formula P equal to P1 plus P2. P is equal to P1 plus P2. Now P value, you know the combination of power, combining power 5 by 4, 5 by 4. P1 also, you know the power of the first lens, it is 5 diopter plus P2. So P2 will be 5 by 4 minus 5. This is 4 LCM, 5 minus 20. So it is minus 15 by 4 diopter. Or you can divide it and keep it. 4 3s are 12, 3 0 4 7s are 28, 2 0 4 5s are 20 diopter. So the power of the second lens is negative. It means it is a concave lens. This way you can calculate the numericals. And keep in mind that the SI unit of power is diopter. We write as DIOPTRE. In short, we write this capital letter D. Thank you and have a nice day. Stay tuned with LFI Educates.